Welcome everybody to the Senior Design 2 project overview. We are Group 7 and we built the obstacle avoidance drone. Our team is comprised of myself, Thomas Hubbard, Nish Patel, Derek Colin, and Matt Izzo. Our motivation for building an obstacle avoidance drone was a strong group interest in drone flight at the beginning of the semester, and we were very excited about the potential for customization with our own aerial drone. The use of aerial drones are very relevant in modern use technology today, and we wanted to create our own beginner-friendly prototype. This video served as some of our beginning inspiration. As you can see, the drone is a quadcopter, and it flies and identifies the pole, and then it will send a feedback to the user interface device where it shows the warning sign that there is an interference detected in front of the drone. Our aerial drone would function very similar. Our goals and deliverables for this project were to create a drone that can safely maneuver through classrooms and hallways. It should be able to detect objects and obstacles within at least 6 feet. It should relay that obstacle data to an Android app. And we should have created a full user interface on the Android app that alerts the user of nearby obstacles in a 1.5-foot range.
Here is a high-level diagram of our system. At the top, we have a Raspberry Pi 5 that was connected with a webcam and 5 time-of-flight sensors. It took the data from those as well as an LED strip for the headlight, and that data was sent to an Android app to be displayed to the user. And the bottom was the flight brain of the drone, which had the SpeedyB flight controller stack, which served as the flight controller as well as the electronic speed controller. And it received data from the RC transmitter and then sent flight commands to the 4 motors. For our hardware design, we had a bunch of components, being the Raspberry Pi 5, the SpeedyB F7V3 stack, a Adafruit I2C multiplexer, time-of-flight sensors that were the ranging modules around the drone, LED light strips, a Logitech webcam, the Android phone to use the app, an N-channel MOSFET that was used to control the LED strip for the headlights, the Ready2Sky motors, a FlySky receiver, as well as an Avionic 4S LiPo battery. For our hardware design, the SpeedyB F7V3 stack was served as both the flight controller and the ECE. It was attached directly to the receiver to get the input data from the transmitter. It also powered and controlled the 4 motors for the flight. The Pi 5 received sensor data from the time-of-flight sensors that would tell the distance around the drone on top, left, right, front, and back. It received live video feed from the webcam to be displayed in the app that you'll see later, and distributed power to the LED strip for the headlights. The Adafruit I2C multiplexer was used to take multiple I2C signals from the TOF sensors and turn them into a single addressable signal to be determined by the Pi for which to be sent to the app.
So throughout the course of our project, we went through many different iterations of a drone model, as you can see in the picture from left to right. We ended with a 4-piece design that was modular and allowed for even distribution of weight. It kept the crucial components secure, and the final design was very robust. So working from left to right, you can see our very preliminary models. They start to get larger and allow for more space for the components to be placed on. The third model you can see is rectangular, which we then had to move to a square model for the 4th. And finally, with these models being too fragile, we landed upon a 4-piece robust frame that was able to be taken apart easily, and pieces could be swapped in and out on the interior. So we went through some trial flights. Our first one was with the rectangular model shown third in the picture on the previous slide. As you can see, this model just flipped almost completely over. So that led to us designing the square model, which can be seen in the second video. So after that crash, that frame broke into pieces where one of the motor wings fell off. So we decided that we had to come up with a more robust frame that would be able to withstand these trial crashes, as can be seen in the third video. So as you can see in all three of these trial videos, the drone wanted to fly off into one direction, and this was due to a lack of calibration of the throttle on the controller. So the stick being in the middle was giving off a wrong value. So after adjusting that value, we were able to calibrate all the motors correctly together and send the correct signal so that we could get even propulsion of the motors.
Like mentioned earlier, we used two different software components. First being Raspberry Pi 5. So the Raspberry Pi 5 actually ran two scripts at once, with the first one initializing and continuously ranging the TOF sensors. The data from the TOF sensors was put through logic to determine whether any of the distances were below 1.5 feet of the drone. And once all this logic and the distances had been collected, they were packaged into a JSON file, which was sent to the Android device. The second script that was run on the Raspberry Pi 5 was a streaming server that was hosted that basically streams live video from the Raspberry Pi and the webcam attached to it. This is later used for the Android application. The Android application features a simple dashboard that basically displays all the TOF distances that were retrieved from the JSON file. It also has a dedicated block at the very top to display whether an obstacle has been detected or not within a 1.5 feet distance. And finally, it also has another dedicated block that provides a live stream of the webcam that is put on the Raspberry Pi 5 and the drone. So here's a simple software state diagram of the software side. So when the Raspberry Pi is powered on by the battery, we go ahead and start the script for the Python script as well as the streaming script. Next, we open up the app to establish connection between the app and the Raspberry Pi 5. Next, the distances begin sensing. Once the distances have been sensed, the JSON file is sent to the Android. The Android receives that file and unpacks it, and then takes the data that was unpacked and displays it to the UI. This process of sensing the data and sending it to the app is repeated until the battery is unplugged from the Raspberry Pi 5, which essentially just turns the entire system off. Here are two examples of our UI for the Android app. So on the left, you see a scenario where there is no obstacle within 1.5 feet. At the very top, there's a green bar that reads safe. On the left, you can see all the distances for all the different TOF sensors. On the right side, you see an example where an obstacle is detected. In this case, it's a hand. This can be proven by looking at the value that reads on the front sensor, which is 1.19 feet. This is because the camera streams from the front view.
To talk about our performance analysis of the hardware, as mentioned before, our final frame is robust and it's able to handle crashes, as during a couple of test flights, it did flip over and hit the ground hard. However, everything was protected and the frame didn't break at all. The frame also protects the interior pieces that are crucial for flight, such as the flight controller, the battery, and the Pi 5 and the breadboard. The flight controller ESC correctly synchronized all four motors. So as I touched on earlier, once we recalibrated the controller, the ESC was able to send the correct signal to all four motors to have them working in combination all at the same time. Our time of flight sensors would correctly measure the distance of obstacles in their view within a small tolerance, and we had a camera that streams a live feed to the Android app.
When analyzing our software, we were able to conclude that the Raspberry Pi can successfully handle both hosting the streaming server while also collecting data from the TOF sensors and also sending them to the Android application. The Android application also properly displays the necessary information and has a pretty constant refresh rate on university Wi-Fi. The Android app also features a pretty dynamic user interface that provides both visual and vibrative feedback to the user when an obstacle is detected. So next, we're here to provide a demo of our obstacle awareness system. So in this first video, you'll see one of our members putting their hand above and beyond the 1.5 feet radius of the drone. You can see the app change pretty accurately as he does so. Next, we'll be taking our model obstacle and putting it around the drone to see how frequently it updates from safe to obstacle detected. Next is an example where you can get an up-close view of the UI as one of our team members put an obstacle around the drone. You can really read all the distances and see how accurate they are and how often they update.
The next two videos are showing flight tests for the final iterations for our model, and this is where we began to have controllable flight. And this is just showing the drone with no subsystem attached. And this is just to test the drone to get it to fly stable. And then here, it shows all the subsystems on board, and we achieve stable flight. And the 360 spin shows how the weight is distributed well.
As far as the strengths and weaknesses go of our drone, the strengths are that there was a robust design that was stable in flight. That was shown from our four-piece design with the metal bolt on all the four corners, keeping it very tight, and the stable flight from the recalibration of the controller to allow for it to fly to the pilot's content, and a modular design that would allow for potential improvement from being able to take out pieces as you like, from taking off the stack of all the 3D printed parts, and a simple and effective ranging technique with the TOF sensors. This allowed for us to get the data quickly and send it over to the Android app, which also had a fast refresh rate that would show the user these values in real time. The weaknesses of the drone was a lack of battery power for the flight controller in Raspberry Pi 5. We found that we had an effective flight time of 4 to 5 minutes, and this was due to our battery not being powerful enough to go for longer. A limited range of being able to fly it away from the transmitter, Wi-Fi dependency for the Android app, as well as we didn't have a trained drone pilot to push it to its limits, and flight areas were hard to find for our tests.
Thank you for watching and listening to our project overview. In conclusion, our project was a success as we were able to build an aerial optical avoidance drone with a working and easy to use user interface. Some future directions that we could take this project would be to further streamline and optimize the hardware design for improved flight and to protect those hardware components. We could find more ways to increase the drone range, drone component range, and the range between the drone and the Android. We could further add flight controls to the Android itself and completely take the FlySky transmitter out of the equation. And we could add more features as well, maybe a grabber, dart shooter, whatever you want. Thank you for listening.